So yeah, I've broken up the talk into these three main segments. And so yeah, first I really have to just run through all the basics of modular slash quasi-modular forms. And once we get through that, then we can start talking about how it connects back to Gromov-Witten theory. But okay, so let's just sort of set the stage by defining what I mean when I say modular slash quasi-modular form. So let's say I have a function from the upper half plane to the complex numbers. And let's say this function is holomorphic. And it's also holomorphic at the point at infinity. Then we'll say that this function is a modular form. So we'll say f is a modular form of weight k, where k is going to be some positive even integer, if f satisfies the following transformation property. So if f of gamma of z, which I'll tell you what gamma is in a second, this is going to be c z d to the k, right? Yeah, f of z. Where, and this has to be true for all z in the upper half plane, and for all gamma in the modular group, so SL2Z. Okay, so that's what it means to be a modular form of weight k.
And CZ plus D is like the denominator of the SL2?
Oh, sorry, sorry, my bad. Yeah, gamma is this, thank you, Maria. And then gamma is acting on the upper half plane via linear transformations, or linear fractional transformations. Okay, and so that's the definition of a modular form. To do things properly, I have to actually get to the realm of quasi-modular forms. So we'll say f is quasi-modular. Quasi-modular of weight k. Okay, so it's going to satisfy some stuff, which will be very opaque, but then I'll make it much more transparent. So if cz plus d to the minus k, maybe I'll say it this way. If there exists holomorphic functions, say f naught through fs, where fs is not identical to 0, such that f of gamma of z, get this right here, is going to be equal to So yeah, like I said, this equation lacks some transparency, but really, I wrote this to be honest about what it means to be quasi-modular, and then in a second we'll really know what quasi-modular means. But I should also say that S is going to be the depth of this function. So we say S is the so-called depth of the quasi-modular form F. Okay, so now let's make this transformation equation more clear. So let's do some.
Can I ask this question?
Yeah.
These F0 through Fs's, do they have anything to do with F itself? Like, is one of them equal to F?
Well, so notice that if S is 0, this implies that every modular form is quasi-modular, because then you can just let F0 be F itself.
I see. So it really is more general. Like you're not making it the F naught through Fs be again like self-referential.
Right. Exactly.
Oh wow.
Yep. Interesting. Yeah. And okay, so but let's make this super clear by doing really hundreds of years of math in a really small list of facts and examples. Okay, so the first one was what I just said to Maria, is that quasi-modular forms are a generalization of modular, but it also respects this weight situation. So quasi-modular forms weight k really do contain all the modular ones. Okay. The next thing is that so given either a quasi-modular or modular form, you can always take its Fourier expansion, and what that means is that basically I'm going to turn this into a different kind of power series, this f of z. So quasi-modular forms admit a Fourier expansion. Oh, is Fourier capitalized now when you write it? It is, yeah. Okay. I just thought it was so common that's not like the Fourier expansion. So in other words, if I give you a form, I can always write it like this, where these a sub n's are complex numbers, but then my q, I've basically done I'm writing everything in the Fourier space, so q is e to the 2 pi I z. Okay, so from here on out, I'll always refer to a form in terms of its Fourier expansion. Okay.
You want to? Sorry,
F of C.
Yeah. F of C that you write at the end of F to the end.
Wait. So I can write. So if I let q be this, then this is really f of z. But then I can think of this as a function of q2 by this substitution, right?
So you're just like renaming it as f of q.
Yeah.
Like,
Okay.
Maybe I should.
like f tilde of q or something.
Yeah.
F of z equals tilde q of q. Okay.
Something like this.
Oh.
Yeah. Okay. Yeah. Is that better?
Well, that's still not no, but that's okay.
Well, yeah. So the long story short, I really want to. From here on out, I'm going to reference the form in terms of the variable q instead of z. That's all. Good. Okay, and so now this weight situation. If I give you the product of two quasi-modular forms, then the weight of two the product is also quasi-modular, and the weight is additive in this way. Okay. And right, so that's really all the facts we need about quasi-modular forms, and now let's actually get to some nice examples. So yeah, like Jeff was saying, the standard examples are the Eisenstein series. So let's define E sub k to be this expression here. Okay, so B sub k, this is the kth Bernoulli number. Okay, and yeah, so far this is just a formal power series in Q, and what is this? So this is sigma sub k minus 1 of n is defined to be the sum over all the divisors of n, where I'm going to add up the k minus 1 powers of those divisors. Good. So this series in Q, this is called the kth Eisenstein series, and what you need to know about them is that, well, E4 and E6, these happen to be modular forms of weight 4 and 6. It turns out there are no modular forms of weight 2, but that's why we have to generalize to quasi-modular forms. But another fact is that every modular form is a polynomial in E4 and E6. Okay. Finally, and then finally, to really not care about this definition of quasi-modular forms anymore, what we really need to know is this: is that every quasi-modular form is polynomial in E2, E4, E6. So for the rest of the talk, this polynomial ring we'll call this the ring of quasi-modular forms.
So in particular, assuming that there's no relations as well.
Right, exactly. Is that right? Yes. Hold on, everything else. There are relations. There are most definitely relations, but I don't care about the relations. I just wanted to declare this the ring of quasi-modular forms. Yeah. Yes, there are most definitely relations. Which I can't think of on top of my head right now, but there are relations. Okay? Good. Ring of quasi. Good. Alright, and let's see what else I need. Oh yeah, so throughout, I'm gonna, yeah, so I'll define, instead of writing this all the time, I'll just write this as QM, standing for the ring of quasi-modular forms, and it'll have a natural grading by weight. So yeah, so Qm sub k is going to be the quasi-modular forms of weight k. Yeah. So just your standard homogeneous grading of this polynomial, right? Okay, good. And now, yeah, that's one. So one last thing, last fact we need before I go on to Gromov-Witten theory is this. So I mentioned delta during the trailer talk, right? So it turns out this is a modular form of weight 12. Okay, so really, if you accept all these 6 facts, then you'll see exactly how I can go from Gromov-Witten theory to this modular form. Okay. Good. Any questions so far? Oh yeah, maybe I should have mentioned that in general, EK is a modular form of weight k. That's what I want to say. K is a quasi-modular form of weight k. Good. Okay, so now let's jump in.
can I ask you a question?
Yeah.
What is this delta in terms of E4 and E6? What's
Ah,
this expansion?
Wonderful question. Okay, exercise.
Well.
Show that delta is 8,000 E4 cubed minus 147 E6 squared.
All right, I'll assign that for homework and I complicated stuff. 247, is that?
Yes.
Wow. Interesting.
Yeah, so one thing I should say is that in the standard number theory literature,
This is not the normalization.
this is
like
the
people use.
normalization we use. But for some reason in the Gromov-Witten literature, they don't normalize, and this is the wonkiness you get. It's much nicer in the number theory setting because then it becomes E4 cubed minus E6 squared over 1728, which is this modular
That's
discriminant, yeah.
yeah.
But
So you just normalize delta by something, or?
you normalize the EKs.
Oh, normalize the yes.
Yeah, and then everything works out. So, but yeah, I don't know. This is a hybrid number theory geometry talk, so I'm trying to.
I mean, there's another way of normalizing things so that, like, you know, E3 and E. Sorry, I'll let you tell.
No, good.
I mean, like, you've got, if Z is the period of the elliptic curve, then if you plug in the data corresponding to your elliptic curve, then when you write your elliptic curve as y squared equals x cubed plus bx plus c, then the b and the c are basically these modular forms, and this are the values of these e things at those at the period. And then the discriminant modular form, if you wire things correctly, is the discriminant of the polynomial f and the phrase y squared equals f of x.
Cool.
Yeah, right. Yeah, it's called the discriminant modular form for exactly the reason that Jeff said. Okay, good. All right, so that's all the number theory I really need. Now let me jump into the geometry and the combinatorics before I connect everything together at the end. So, all right, let's now, yeah, so the way most moduli curves talks go is I'll say let G and N be non-negative integers such that 2G minus 2 plus N is strictly possible. So first let me, so is it, can I start with defining stable map? Is that a solid, have people encountered stable maps before in this audience? Probably. There's a good chunk that haven't, right? So,
Feel free to tell me.
okay, great. Okay.
We have grad students. So remember what you know in your first year.
Yeah. Okay. Sorry.
That's cool.
Yeah. So okay, let's say I have an algebraic map.
But also remember how useful it was in your first year of grad school when somebody defines stable maps.
Yes. Okay. Okay. It's all coming back to me now.
Just do it the right way.
So right, let's say I have a algebraic curve of genus G, which I'll call C sub G. Let's say it's at worst nodal, and the other data is I have n marked points that are smooth on this curve. Okay, and so if I have a map from such a curve to say a smooth projective variety X, I'll say that this this morphism is stable if it has the following property. So if whenever f contracts a rational component or a genus0 component, actually rational irreducible component, say C naught containing CG. So when I say contract, I mean the map F just sends that whole component to some single point in the target. Then whenever this happens, C naught, this irreducible component, is incident to at least 3 special points. And so when I say special points, I mean either some of the smooth marked points or a node. Because we said at the beginning that this curve is at worst node. Okay. Good. So now, with that, I can define the moduli space of stable maps.
But also with the elliptic component with one special thing.
I think this condition already
Okay.
fixes that for you, right? Okay. So now let me. So here's the notation for the moduli space of stable maps to that. So E is going to represent a smooth elliptic curve, and D is going to be essentially a homology class on this elliptic curve. So yeah, let me tell you what I mean. So maps this such that
E probably.
what's up?
X is E.
Oh, yeah, sorry. Thank you. To the smooth elliptic curve E, such that this dot in stable map literature usually means we allow our nodal curves to potentially be disconnected. So this curve here is possibly disconnected. Okay. The second condition is going to be in reference to this D. So if I push forward this curve class, or this curve, I get the homology class D. So in this case, since E is a curve, we can just assume D is some non-negative integer. And finally, at this state, of course. Okay, so these are describing the closed geometric points of this moduli stack. And right, so we have to be careful about these things. So the space is a, how do I want to say this? Yeah, so this is a virtually smooth Deligne-Mumford stack. So I'll talk about this in a second. I'll just mention why I have to say it this way. Virtual dimension. Two G minus 2 plus n. Good. So yeah, so I'll in a second I'll make a definition that really sort of brings the point home why I have to say it in this way. But let me first introduce some stuff, some maps that come with this space.
Wait, so CG is genus G, but it's possibly disconnected. What does that mean?
Right. So okay, I always have to be careful about this because the Euler characteristic is additive. So
So it's like the same thing in terms of the Euler characteristic. I just have to I'm just
Yeah.
wondering how I envision the number of poles when you have disconnected components.
right.
You add up the genus and subtract 1 if they're disconnected. There's 2
Yeah,
components.
every time you add a component, you subtract 1.
Okay.
Yeah.
Okay. Sounds good.
Okay. Thanks. Okay. So this moduli space, it comes equipped with something called evaluation maps. So we have EV1 through EVN. Okay, so these are maps from the space of stable maps to the elliptic curve. And what they do is they just tell you where does the ith marked point map to. So finally, we have these so-called descendant classes. And a descendant class is a first Chern class of a certain line bundle on this space. If you're familiar with moduli of curves, it's the same exact idea. You're taking the cotangent space at the ith marked point, and then forming a line bundle and taking a Chern class. We also have psi 1 through psi n. So these are in, say, the first Chow ring, or the codimension 1 Chow ring of this space. Okay, and psi I is the first Chern class of the line bundle whose fiber over the point in moduli is the cotangent space at the ith marked point. So in particular, I'll write it this way, the fiber over a map, over a stable map, happens to be the cotangent space to the curve at the ith marked point. Okay, so I have these classes, I have these evaluation maps, and now I can actually define what I mean by Gromov-Witten invariant in this talk. So the stationary descendant Gromov-Witten invariance of the smooth elliptic curve E is defined, so they are, so there's many of them, are defined to be the intersection numbers defined in this way. So I'm going to use this notation bracket tau k sub 1 through tau k sub n. Okay. So this notation is going to mean, so integrate over a virtual class and then in the integrand I have this pull back the class of a point along all the evaluation maps and then put in these psi classes corresponding to these k lines. Okay, so now I can actually say something about this. So
I'm sorry, I'm kind of a thug. Like, what kind of object is that? Is that a number, or is that a cohomology class, or what is it?
yeah, this is a rational number.
Thank you.
It's a rational number. And okay, but yeah, now I can say something about this. So yeah, so this Deligne-Mumford stack is not smooth because it has these components of varying dimensions, right? However, it's virtually smooth in that we can find something called a virtual class. So it's essentially an element in cohomology that satisfies all the properties you would like it to have. You would like a fundamental class to have, of which you can integrate against in a consistent way to get these intersection numbers. And so that's really sort of the main point of saying this. But okay, so now, yeah, so it's great that Jeff answers, yeah, because you stare at something like this and you say, what is the point of this, right? And so, but I think the first punchline is that even though this looks sort of this abstract consequence of all these definitions, this next theorem says you could really sit down and compute these by hand if you really wanted to. Okay, there's a nice closed formula here. So,
what is the part for stationary?
Okay, what is, yeah, well, so the stationary comes from the fact that we're pulling back a class of a point along each marked point. So you're restraining the stable map to map the n marked points to some fixed set of points. Yeah? And then the descendant part comes from the fact that these are called descendant classes. Good. But yeah, so now first punchline is that this guy, even though it looks abstract, is very down to earth by a nice closed formula due to Wulkenhaar and Fourier. Okay, so the first theorem is due to how much time do I have? Okay, you said 4:15 is okay, right? Okay, so the theorem says that this rational number can be computed in a completely combinatorial way. It's the following. It goes, so 1 over the product of a bunch of factorials between the ki's times the sum. So yeah, I'll write some things, and then for the grad students who haven't seen some representation theory, I'll explain everything in a second. But let me write this all down. So this is the, okay, let me write this down and then I'll say a couple words about what I mean. Okay. So this is the closed formula for this intersection number. And what is it? Well, okay, so first of all, it's a sum over partitions of the integer d. That's corresponding to the degree of these stable maps. But what is everything else? Well, z lambda. So if you've taken some representation theory, then z lambda happens to be this quantity here, which has a very group theoretic interpretation. So let me write it. I'll say what it is. Okay, so what is this? So m sub, so this is a sum over partitions of a number d, right? So m sub I is the multiplicity of I. It's the number of times I shows up in the partition. Okay, and then take a product of factorials. Okay? And then this is just the parts of the partition. Yeah. Okay. And so if you've taken some rep theory of symmetric group stuff, then you'll recognize this as the order of the centralizer of the conjugacy class corresponding to a permutation of cycle type n. Okay, so it's a very group theoretic slash combinatorial object here. Okay, what is okay? Now you really have to go into the weeds of representation theory for the chi's. So what does chi lambda mean? Well, I can't say too much about it because then this would take forever. But let me just say that if I give you a representation of the symmetric group, right? There's something called Maschke's theorem that says I can always break it up into a bunch of irreducibles. If I give you an irreducible, so the irreducible representations of the symmetric group are in bijection with partitions of D. And for each irreducible representation, you can take its trace, because we're talking about matrices and mapping into GLV, and that's called a character of that representation. Okay. And so these are the characters corresponding to the irreducible representations of SD. And chi lambda mu just means take any permutation in the conjugacy class corresponding to cycle type mu and plug it into chi lambda. And this is independent of which representative you take. So that's what I mean by chi. But the long story short of this is that this is a purely combinatorial thing to compute. You can really, there's a nice thing called the Ramanujan rule, which says you can compute this guy recursively based on border strips of Templa, all this things. Okay, So far, you're like, what in the world does this have to do with elliptic curves? I don't know, actually. This is kind of mysterious to me that we're still talking about something, you know, maps into elliptic curves, and we get these nice characters out of it. Oh, yeah.
But this, just to make,
Yeah.
sorry, I'm just dumbing it down, but this thing doesn't actually depend on the choice of E, does it? Like, it's just
No.
whatever it is? And
Right.
Okay.
Right. Yeah.
Oh, wow.
And then finally, this bit here is, okay, so I'll write it down. So piece of k of lambda, what do I mean by that? That means it's this, okay, it's a sum, it looks like this. So I plug in a partition lambda and so lambda I minus I plus 1/2 to the k minus I plus 1/2 to the k. Okay,
Wait,
so
and
that's...
is G in this formula anywhere?
No, because, yeah, so the expected, so once I tell you what the psi's are, then the G is automatically determined by, once I tell you what the psi's are and what the degree is, then G is automatically determined from the dimension constraint of this module.
Oh, I
Yeah.
see. There's like a formula. Okay.
Yeah.
Interesting. Wait, the K1 through Kn is like what they add up to, is what you're saying?
Yeah, exactly.
Ah, okay.
Yeah.
They add up to like something. Okay, that's what it is.
Minus, okay, get this out. So root times 2k. Okay. So we have this thing here, piece of k of lambda, right? So this looks like this random sum here, okay? But actually, so these are called, these p's are examples of something called shifted symmetric functions, okay? And they come up there. So there's the classical theory of symmetric functions. You can deform this ring, the ring of symmetric functions, and get something called the shifted symmetric functions. This is the work of Wulkenhaar. He used this to prove something called the Bloch-Wulkenhaar theorem, which is not what I want to talk about here. Really, I mean, the point I want to make is that this is just a very simple looking expression in terms of the partition lambda, right? And okay, so the long story short is that this guy, with a little bit of patience with hand and very less patience on a computer, can compute this no problem, okay? But the really magical part is that you can go from all that combinatorics back to number theory because there's a theorem that says that if you look at all of these intersection numbers and you stitch them together in the following way,
Theorem in the same paper?
what?
Theorem.
Oh yeah,
same
this
paper?
is also a concurrent under. Oh, yeah.
Okay.
So yeah, so if you take all of these intersection numbers and you stitch them in this very peculiar way, and this is a quasi-modular form of this weight. Sum across ki plus 2. Yeah. Which is, yeah.
Are these, this is probably, I don't, maybe I should know this. Are these things integers?
Which ones? Oh, these ones?
Yeah,
These are rational numbers. Yeah.
but they're not integers.
They're not necessarily integers, right?
Right, I mean, we can see they're rational.
Yeah. Yeah. Right. Yeah, and something that'll come up later is that the Ramanujan tau function is always an integer, and yet by some miracle something's going to happen to make all of these rational numbers add up to get an integer.
Okay. Because the modular forms, a lot of times you get integer coefficients, right?
Well, for
Or maybe, quasi-modular, sorry.
quasi-modular forms, you
Yeah.
can get some rational.
I see,
Yeah. Because of how I divide my EKs too, right? So.
Mhm. Oh, right. Cool.
Okay, so this is it. So this theorem is how I can really talk about quasi-modular forms in terms of Gromov-Witten invariants. Okay? And, well, okay, now there's a lot of questions. Because the question is, well, just because this lies in this set doesn't tell you anything about whether these, these generating functions really generate this entire ring, right, for any weight. And it turns out that they do. Well, I conjecture that they do, and I have a lot of evidence for this. Okay, so good. So let's.
What happens if you add up all the these tau products over all the k compositions?
Say it again. If I add up.
If you add like all these tau k1 through tau kn things, but if you add up all of those functions over all possible k1 through kn choices.
Oh.
Like if you add up all those quasi-modular forms,
Yeah,
you get like a modular form or something.
I don't know actually. I don't. Is such a sum even makes sense?
Full descendant potential.
Yes, you get the full. So yeah, you get this master generating function called the full descendant potential of the elliptic curve. Right, and then these full descendant potentials always have these. They always satisfy all these really nice differential equations and stuff. Yeah. But I don't. Yeah, I haven't prepared that.
Okay. No, I was just curious.
Okay. All right. But now, okay. So we have started from Gromov-Witten theory, and we've landed in quasi-modular land because of this theorem. But what can we do with it? Well, first of all, so now let's go to the final section, which is about quasi-modular forms and these. So I'm going to call these stationary descendants of weight k. So let me write this down. Okay. So definition. So such a generating function will always be called a stationary descendant of weight k. Okay, so the first theorem that I want to mention is that, right, so the first thing you might ask is, well, how good are these generating functions at generating the entire ring of quasi-modular forms? Turns out it's not that bad because so the entire ring of quasi-modular forms.
So what you're defining, or
What's up? I'm just defining whenever I have this. Oh, sorry. What do I mean by k? So k will be the sum of the ki's. Yeah. Plus 2. Yeah. So the first result is that the entire ring of quasi-modular forms can always be generated by the following triples.
I'm just confused. Is that Hans result or defining?
This is the definition. So this is just the definition, and this is the result.
It's just defining K. First definition. K.
Defining K or
K is the sum of the Ki plus 2 from 1 to n. That's essentially the content of that
because
definition.
you just said that in the theorem that the left-hand side is weight is equal to that, right?
Yeah, so it's going to call that K.
Okay.
The content.
Yeah.
A stationary descendant of weight k is a thing on the left-hand side of that.
I see. Okay.
That's
I
what I
see.
think he
Yeah,
said.
all right.
Yeah. Okay. So the first thing is that you can get any quasi-modular form you want from any triple of stationary descendants in weights 2, 4, and 6. Okay. So this is really any triple is in weights 2, 4, 6. Okay. So, for example, because this is true, that means in principle I should be able to write the discriminant modular form in a bunch of stationary descendants, right? So here's one way you can do it. So delta happens to be this. Let's take it. 1. Minus some stuff. 2 tau naught cubed squared. Sorry, I'm almost done. It's only 7 terms, right? Almost. Cubed tau naught plus 5, 1, 8, 4. Tau naught plus 1, 2, 3, 4, 5, 6, 7, 7. Good. Finally. 2, 8. Hey, my little experiment showed up. Wild. That's nice. Okay, so there it is. If you use this theorem and you say, okay, this theorem says I can write every modular form in particular in terms of any triple of the stationary descendants, and you work out the math and you say, okay, this is the expression. Okay. All right. So, so in other words, Ramar's conjecture says this generating function has non-vanishing coefficient. Okay. Which is okay. Oh, well, so how could you approach Ramar's conjecture that way? Well, it turns out that so when you look at the stationary descendants that look like this, tau 0 to the n.
Can I ask?
Yeah.
Why did you put parentheses there?
Like this one. Yeah, these are all the things. Yeah.
It was just.
So another way to phrase Ramar's conjecture is that the degree d coefficient of this thing can never be the same as the degree d coefficient of this. That's another way to say it. Okay. But actually, when you stare at this and you really try to figure out what's going on, then it turns out everything becomes so you turn a really hard number theory problem into a much harder combinatorics problem. Because, but yeah. So let's find out. It turns out that these stationary descendants happen to always be this. So in other words, yes, this is a little lemma. You can, well, I proved it in my recent preprint. And P of D is the number of partitions of the integer D. So in other words, if you try to plug all these things back in, then you get this really, you're basically saying you're getting a complicated, you've turned Ramar's conjecture into a complicated statement of this really complicated expression of partitions can't do the same as the other. Oh, what do I mean by this? This Pockhammer symbol is okay. Good, but one thing about this expression is that you'll notice that because this theorem tells you that you have a bunch of powers of this Pockhammer symbol here, and there's something called the pentagonal number theorem, which says that when you just have a single power like this, a q sub infinity, there's a closed form expression for this. So for the degree d coefficients of this power series. So this happens to be. So that's right. Every integer d. Okay. And so, yeah, so when you have a single power of q infinity, then you have this nice closed form expression, so you can extract the degree d coefficient really easily. It's not easy when you have powers of q infinity. There is no, so this is called the pentagonal number theorem. And there is no pentagonal number theorem for higher power than q infinity. If there was, then you can actually make a lot of progress in approaching Newton's conjecture from this expression. However, what you can do, you can get around this by saying, well, can I express delta not in a non-linear way in terms of stationary descendants, but in a completely linear way, where I only pick up single powers of q infinity? And it turns out the answer is yes, you can do that. And in a very combinatorially symmetric way.
What's P of D?
P of D. Oh, sorry. Yeah, this is number partitions of D.
I mean, you can always take the pentagonal number theorem to a power and just sort of expand, and you do get something. You know, combinatorial. In terms of like, how many ways can you write a number as a sum of pentagonal numbers? And, like,
Right. Yeah, that's true.
I don't know
yeah.
how, you know, I don't know how nice it is. It's just like, you can always expand.
Mm-hmm. Yeah. But then, okay, but for example, on the right-hand side of this expression, I think you'd have up to you'd have up to like a sixth power of this, which is already pretty gnarly. Trying to expand that and using pentagonal to write that down explicitly. Okay, but yeah, so like I was saying, you get around this powers of q infinity situation by essentially asking yourselves, can I write delta just linearly in terms of stationary descendants? And it turns out you can. So I'll end here. This is the last thing I'll say. So it turns out that if I look at all quasi-modular forms of weight 12, then I can always generate it in the following way. So I'll call it ABC. Where actually not just three things, but maybe a collection of all of them. Collection. Stationary descendants. Where the sum, and this is actually weight 12. So that's the first thing. So it turns out that even if you just look at all the possible stationary descendants of weight 12, that will completely generate the weight 12 quasi-modular forms.
But as a ring, because you said this graded, like, I'm confused.
Sorry. So yeah, you're totally right. Yeah, I should say it like
The
this.
vector space? Or?
Yeah, exactly. Yeah. Thank you. Thanks. But so yeah, so this is the first result. But even to make life so, you might ask yourself, well, how many stationary descendants of weight 12 are there? There's 21 of them. That's a lot. Okay, so that's saying that this there's a map from this 21-dimensional vector space to this much smaller vector space. This happens to be 7-dimensional. That has a really large kernel. Okay, but you can do it a little bit better. You can actually I can also show that, yeah, so it's the same thing. So sum over all of the stationary descendants of weight 12, but with the restriction that the insertions have to be strictly positive. Okay. And so there's only 9 of those guys, so really we've reduced the kernel by a lot. Okay. And so how many, yeah, actually we can explicitly write down all 9 of these
So the
stationary descendants.
upper one is sigma, and then the lower one is direct sum, correct? Because you said that there's a relation, so
Yes, the span of those things?
Yeah.
yeah. So it's the
But
sum.
They're
sigma,
not
and
linearly
then-
independent.
Oh, yeah, they're
People are
objecting to the
direct.
circle around the plus.
Ah, okay. So you want me to turn this into a sigma, and this one into a well.
They're both sigma.
Okay, asking.
They're both. Oh, they're asking me. Okay, no, they're both sigmas. They're both sigmas.
So
Yeah,
there's okay.
The one in the bottom is a little less sigma than the
Right.
So dimension is less than 9 then.
It's 7, he said.
It's 7.
Yeah.
Yeah.
But you said that something is 9 of them.
This is
The right hand
Sorry,
side.
maybe.
yeah.
The first one.
The right hand side is 9 generators, the one on top is
21
21
generators.
generators.
Yeah, that's what I'm saying.
Span
Yeah.
7 dimensions.
Yes. So, for example, what are all the 9 descendants of weight 12? They have that have only positive insertions. Well, I can write all of them down for you. They are here. So, and this is the final last thing to say. There's 9 of them. 6, 10. Stationary descendants of weight 12, and it turns out that any 7 of them will form a basis for the ring of quasi-modular forms of weight 12. Or in other words, this is the phenomenon of a uniform matroid. And there's a lot of questions that there's a lot of directions I want to take this in terms of determining when the matroid is uniform in this way, and there's a lot of, but the last thing I'll say is that because any 7 of these form a basis for QM12, then I can write delta in basically 9 choose 7 different ways. And so maybe one of those 9 choose 7 ways will be the one that will knock down the inverse projection. Who knows? But I'll end there. Thanks.
Any questions?
So for the one in terms of, the formula in terms of all the tau knots, you had this lemma on how to expand it. Do you have lemmas like that for each individual one
No,
of these?
yeah, that would be the next step. To
Yeah.
see if you can find a nice combinatorial expression for those guys like this.
Yeah. And
That's
have you tried expanding those maybe just for like a family of certain coefficients you can prove are non-zero by like rounding things? I don't know.
So that's the other strategy I'm trying, which is basically try to find really tight bounds on the irreducible characters
Yeah.
and the symmetric partial
Yeah,
sums.
yeah.
Because if you can really, then you separate the positives and negatives, and then you get this.
Oh, yeah,
Yeah. And then you could say that the absolute value of tau of d is bounded below by
Yeah.
something, and then you win. But that's a really.
There are some bounds on the characters, that are.
Really?
Like the chi values.
Okay, I didn't know that. Okay.
Yeah, well,
That's
yeah,
good.
people have studied those things.
Okay.
I don't know about the symmetric, the
Right.
symmetrics,
Yeah.
the shifted symmetrics, I don't know those. But.
Okay.
So that is that just a example or a lemma?
The theorem is that I can always do this for any set of descendants in weights 2, 4, and 6, right? And I can always find some expression, right? And then you just do some linear algebra to figure out what the expression is. Yeah.
Any intuition or geometry intuition why there's only like tau naught? Sure.
No, this is just one example. So
Okay.
yeah, it's like you could. Here's a triple of stationary descendants in weights 2, 4, and 6. But there's another. You can also do the triple. This is a stationary descendant of weight 4,
Oh,
and so I can find delta in these 3 generators too.
Did you try tau naught, tau 4?
Yeah, it's somewhere my favorite.
Okay.
Yeah.
Is it-
Okay,
Does-
so
does,
one thing I'll say is that what's really peculiar is that any triple you choose, you always get integer coefficients in front of the monomials too, which I can't. A priori, you shouldn't expect that. You should just expect rational numbers. But yeah, I've stared at all the ways to do it. I've stared at all the ways to do it. I haven't found a way yet.
But this one's modular, right? The
Yes,
delta.
exactly.
But
Yeah.
you're using the two, like the modulars can be generated by a 4 and a 6, right?
Yes. Yeah.
But you're using a 2, 4, and a 6 to,
Yes, exactly.
even though it's modular, not quasi-modular.
Well, when you expand delta in terms of E2, E4, E6, there is no E2. We saw at the beginning that delta is just E4 cubed minus something minus E6, something E6 squared, right? But the magic is that even though these individual terms are quasi-modular, by some cancellation, everything there's no E2 term when you expand this. Yeah.
Uh-huh.
And that's the other thing actually that I want to understand. If you give me an arbitrary expression of stationary descendants, is there a criterion to say, oh, this thing's actually modular?
So if you want to make E4 or E6 with your descendants,
Yeah.
in particular you need to use tau naught.
Need to use what?
Tau naught, so you need to use this sort of quasi-modular, some polynomial and quasi-modular of the taus to get.
Yeah. So wait, one thing so tau naught is just E2. That one we know that. Yeah. So
Up to some constant, right? That had to be, right?
no, this one's dead on.
Okay. Yeah. Okay.
Yeah. But your question is.
So E4.
Yeah.
Right? So in principle, it should be sort of like a polynomial that has some tau naught square term, right?
Yeah.
But one could say, okay, could I make E4 without using the quasi-modular one? Sorry, using only things of weight 4.
What can you use?
Like so tau.
Oh,
2 and tau 1.
using I see. Yes. Well, conjecturally, yes.
Okay.
Yeah. I mean, I've done it for very low weights, like E4, E6, E8, and stuff. You can always write those as a linear sum of stationary descendants of that weight.
Of that weight.
Yeah.
Okay.
But I don't know how to prove it.
Okay. So it's not like you need to use the tau naught necessarily.
Right.
Are any of the stationary descendants actually modular?
Like I mean, just on its own, not some complicated.
Just, like those single things.
I think that's an open problem, actually. I don't know. I think we know that. I don't think we know that. Yeah. I'd be surprised if you had some really high weight stationary descendant that was actually just modular. I'd be very surprised.
You know that like the ones that you studied are not.
Yeah.
There's no more questions. Let's thank Adam again.